Hi, it's time for another Math Easy solution. Today we're going to discuss further into the seasonal growth models for population growth series on differential equations. And I'll look at example 2 of the seasonal growth video series and look at part A of it. And part B I'll do in a next video, so stay tuned for that. Basically, this one is basically we're going to modify the last model that I went over in example 1. So let's go over the example. So suppose we alter the differential equation from my last video, example 1, as follows. So again, make sure to watch example 1. So this is in fact the exact same as example 1, except there is this squared factor right there. That's the only thing we're doing. We added the square cosine. The other one did not have the squared. Yes, so anyways, a differential growth model here is dp over dt, p is population, t is time, equals to k, that's just a constant, times p, times cosine squared of r, another constant, times t minus phi, which is another constant. And then we have the initial population p of 0, that's just p0 or p naught. And so part A states solve this differential equation with the help of a table of integrals or a computer algebra system, and part B involves graphing the solution of this for different values of the constants and comparing them, and also finding the limit as t approaches infinity of this of the solution to it from part A. So we'll do part B in next video. So part A I'll do now. So instead of using table of integrals or a computer algebra system, I'll just do this more of a manual way, just because it's a good exercise in mathematics. So let's write this down. So dp over dt equals to kp cosine squared rt minus phi. Let's see if we got that right. Yep. So again, recall that we're just dealing with a separable equation, because we can move the p onto the left side and the dt onto the right side, so that we have all the p's on the one side, all the t's on the other, and then we can take the integral. And again, this is just part of the separable equations solution, how you could solve them, and you can learn more in my earlier video in the description below on separable equations. So we move that over, we get dp over p equals 2k cosine squared rt minus phi dt, like that. Let's write this like that. Now we could take the integral on both sides. The left side, it's a pretty standard integral, as is ln absolute value of p. But the right side here, this isn't as straightforward. You could use a table of integrals, or I'll just use instead of that, I'll just use the trigonomic identity here. So recall from my earlier video, and I'll put the link to this proof in a video link below. Recall the trig identity, or trigonomic identity, which was cosine 2x equals to, this equals to 1 minus 2 sine squared x. And also recall the basic trigonomic identity, sine squared x plus cosine squared of x equals to 1. So if we rearrange this for sine squared, we just have to move this to the right side. So we'll have this, we'll have sine squared x equals to 1 minus cosine squared x. So now what we could do is combine these two, throw this in there. Let's put this. So we would throw this sine squared for cosine squared x, because we have cosine squared. And what we want to do is remove the squared symbol, or the squared, so we could just get we just deal with cosine without the square, so that, and we know the integral of that, which is just sine. So we just throw this in there and then bring it down here together. We get finally we get cosine 2x equals to 1 minus 1 minus cosine squared. That's a 2. Now we just plug it inside here, and then 2 squared x, like that. Simplify this. This equals to 1 minus 2 minus, this is negative 2 times that. That's plus 2 cosine squared x. So this is going to be -1, but then we'll just move this over to the other side, so that what we end up getting is cosine, let's put the 1 in front, so 1 plus cosine 2x equals to 2 cosine squared of x, or just divide this by 2, and we get this. So that's another trig identity. I just wanted to go over that one there. So now we could replace this cosine squared here with 1 plus cosine 2x over 2. So, yeah, so what we get now, let's just write this all down. So what we get is integral of dp over p equals to, and we can just remove the k constant outside. And now this is this cosine squared. So we'll be writing this as 1 plus cosine, and also there's a 2 there. I'll take a 2 out of there, just a constant. So this is going to be cosine, and I'll put a bracket 2, and then this is going to be RT minus phi. So instead of x, we're dealing with this RT minus phi. That could be our x, and then we're just applying that identity to this form of it, like that. So we get something like this, and then we have dt. Let's double check it again. Yeah, so this is cosine squared becomes 1 plus cosine 2 RT minus phi, and remove the 2 outside, just a constant. So now we can take the integral. The right side's going to be ln absolute value of p. That's the integral of that, and you can see more on my earlier videos on that, proof for that. So then we have to always add a constant of integration c1, and then we also here, this is the integral. This is going to be k over 2, and then the inside of this is going to be t plus, and what we have here, the integral of cosine, that's just sine, and then we have to write, I'll just put this bigger, just bracket like that, so it alternates from bracket, square, regular bracket, etc. So RT minus phi, like this. So this is the integral of it, but we have to apply the chain rule, and so then we have to divide by 2r, because the derivative of sine 2RT minus phi is going to be cosine 2RT minus phi multiplied by the inside chain rule, which is going to be 2RT. The derivative of this whole thing, this one is just a constant, goes to 0. The derivative here will be 2r, so we need to divide by 2r. And then plus constant of integration c2 for the right side. So now what I want to do is, since we are dealing with growth, we don't need to look at the absolute value. Dealing with, I'll put quotation mark, growth, we're not going to look at a population that's negative. So p is greater than 0, and when what we have is ln absolute value of p is going to be equal to ln absolute, or just ln p, because this is greater than 0. So we could just write this down as ln p, and also move this c1 onto the other side and combine the two, and I'll do that soon. So what we have, and then multiply this out as k over 2 t plus k over 2, but there's a 2 there already, it's going to be 4, and there's an r there as well. And then we have the sine 2rt minus phi, this is the Greek symbol, phi, Greek alphabet letter. So, and then plus c, where we combine the c2s and c1. So where c equals to c2 minus c1, and this is just a constant. A subtraction of constants is still a constant, like that. Let's write this one neater. Okay, so now that we have this, now that we have this, we can, let's solve for c, since it's all separate by itself, instead of solving for p right away. So let's solve for c. And we know that basically at p0, the initial population, we're just terming that as p0 or p0. So what we get is ln, then we just plug that in here. So ln at time is equal to 0, ln p0 equals 2, This is k over 2 times 0. T is 0. You can also note it's the same thing as writing p. T equals to 0. So that's a 0. So 0 plus k over r, k over 4r. And then we have sine, what is it? Yeah, sine over, sine times it by, I put this bracket like that, 2 times 0 minus 5, so that just goes to 0, the RT. So we have, this is going to be negative 2 phi, because we end up having, what we end up having is just this, this 2 times negative phi. And then plus c, constant. So now before we solve this further, recall my earlier video I went over basically, I'll just graph this out. Basically, when you have the sine function, a negative sine function like that, when we're dealing with it, this is how the sine of x function looks like. And then when you, at this point, this is at equals to 1. At this negative side here, this is negative 1. As you can see here, if you were to graph it, just flip this over, so make this sign negative. So if you made every single thing here negative sine of x equals to negative sine, just put that like that. Because here at this point here 1, you go to negative 1, and then here you flip it. So when you have negative sine of x, notice here what you have is this is actually an odd function. It's symmetric, and it's the flip of the sine of x. So in other words, at this point here is pi over 2, and at here is negative pi over 2. So then at this point here, this equals to negative sine pi over 2. Here, this is just, at this point here, this is just sine pi over 2, or negative pi over 2 inside. So that's just an illustration, but if you want further proof, make sure to watch my earlier video on that, and I'll put that in the video link below. So what this means is basically sine negative x is equal to negative sine of x. And you can go through basically every other point. This point is going to correlate somewhere over here, negative of it. It's just going to be negative. Anyway, so what this means is we could take this negative out of the equation. So, I don't know what happened there. So we have this ln p0 is equal to negative k over 4r sine 2 phi. Let's just write this down, check it. Yeah, so the negative goes out. We have this negative k over 4r plus c. And now we can move this over to the left side. What we get now is c is equal to ln p0 plus k over 4r sine 2 phi, like that. Okay, so now that we have that, and we can throw the c inside this giant, inside this equation right here. So what we end up getting is ln of p is equal to, let's see if we remember this one, I think it was k over 2. Yeah, k over 2t. So this is just a giant equation. K over 2t plus k over 4r, and what I'm going to do is put this giant bracket around. Let's put it like this. Sine, and then because we're going to plug in this, we're going to plug this, factor out this k over 4. Actually, we'll do that afterwards. Why is it a 3? So let's just do this regularly. Sine, this is going to be bracket 2. Yeah, this is just really tedious stuff. 2 minus r t minus phi, and then we have to add down the c, which is plus ln p0, and then I'll just put this here, I'll just go further, plus k over 4r sine 2 phi. Yeah, so this is the c constant that equals to c. So we add that there, and now what you notice is this is a ln p0. We can move this over here and then apply logarithmic property of whenever you're subtracting logarithmics of the same base. This one's ln is log base e. we could divide. When you subtract, you can divide the terms inside. So, and you can learn more about this in the video link below. So this equals to ln p over p0, and this equals to k over 2t, and then now we can factor out the k over 4r with this. So we get this k over 4r, and then sine 2rt minus phi plus, and then we factor that out, sine 2 phi, like that. So now we could take both of these and make them as a power of e to get rid of this ln. But before we get to that, what I'll do is I'll let this side equals to f of t. So I'll just circle this whole thing. So I'll write this as a function of t, just to simplify it, so that there's a t there. So then what we end up having is ln p of p0 is equal to function of t. Just to simplify things, take both as a power of e, and then this simplifies to, so I'll put that over here. This becomes ln, the lns cancel, so we get p over p0 equals to e of f of t. Move the p0 onto the right side, so what we get is, and I'll move it here just so it's close to that, we get p of t is equal to p0, p initial population, times it by e to the power of this function of t, f of t, which is connected to this one, instead of writing that all down. So that is our solution. Yeah, so it's pretty complicated, or just pretty long and a bit tedious to write that all down. So we'll just simplify it with an f of t function like that. So that is, that's the solution to this modification of that seasonal growth model from example 1. So hopefully you enjoyed and followed through this pretty extensive but pretty interesting mathematical exercise in deriving the solution. And in the next video, part B, stay tuned for that. I'll go over the solution, graphing it, the solution, different values of k, r, and phi, as well as looking at what happens when the limit as t goes to infinity of the population. Anyways, that's all for now. If you enjoyed, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.